Hello, welcome to module number 3. In this module, we are going to discuss about deconvolution, 3D visualization and colocalization analysis. If you take an image using a microscope, what you will observe is that the image is not going to be as simple as you thought, that you have just a spot here and then it will be producing an image like this, which was supposed to be a spot, but it forms a weird structure like this. It is called point spread function. This happens because the light gets diffracted from the edges of the optical elements in the microscope. We cannot avoid that because there is a certain diameter of the lens, and hence the size of this function here will be determined by the size of the lens and many other parameters. Practically, this is of the size of a few microns or a few hundred nanometers. The best one can get is the tiniest one will be like about 250 nanometers. So we have to deal with that. And how does it affect our image? As you can see, this spot has been converted into this weird shape. So if we have a lot of spots like this in the image, they all will be convolved with the point spread function to form a image like this. So how does it affect our image practically? So this is the original image how it was supposed to be, but because of convolution of the point spread function, or basically distortion of the original image, you get an image which is like this. A lot of out of focus light, a lot of different overlaps that are happening, and many more artifacts that you see. So there is a mathematical process called deconvolution, where you take an image of a bead or a sample which is known to be spherical, and then you get the image like this, and from that you already have the image which is like this from the microscope, and you have an image of a bead which is spherical in nature and it is producing image like this. So you can calculate back what was the original object. In this case, this is the image that you acquired from the microscope, and you can mathematically calculate back what would it actually look like. But of course, this is not the best method. There will be some bit of artifacts that can come in, because no mathematical calculation is going to produce the best actual original image, but this is getting somewhat close to the original. Okay, so let's see what did we how can we apply that in our research. So this is an image which was provided by Zhuangxi. We are very thankful to him for helping us with this image. This is an image where there's a thin film of oil over a metal surface, and that has been labeled with a dye. When we image it on a multiphoton microscope, what we observed is that instead of getting one single plane, we were getting multiple orders of intensities, and this intensity was also spread around z-axis. So we were wondering why did this happen. So we imaged a bead using the exact same optical settings on the microscope, and what we found out is that the bead image was also like a little weird. You can see that this is stretched in the z direction and has got multiple orders like this, and there's a little bit of background also. So what it means is that the actual thickness of this oil layer that we were trying to measure is not actual. It is convolved with the point spread function. So how can we calculate it back? So using the iterative deconvolution method available in ImageJ, you can do it. This is the image, this is the second image, and using that we calculated back, and we could actually get very close to the whatever was the theoretical limit of the size that we were expecting it to. So this is the image from the this is the plot line profile across this image, and you can see that it's very widespread and very noisy, and there's spread around here. But the moment we deconvolved it back to original, we could get a very tight image like this. So this shows the power of deconvolution. So if you want to practically do it and try out this test on your sample, the way to do it would be typically Fiji or ImageJ doesn't have the module called deconvolution available in it. So what you have to do is to go to do Google search and look for ImageJ deconvolution, and you will come across this page. And here, if you go down here, there will be somewhere iterative deconvolution. If you click this, it is going to take you to this page. And here you can see that they have given you exact protocol on what to do, what not to do. So what I did was to download this class file, iterative deconvolution 3d.class. Downloaded that. It will download like this here, and then take this file and open save it in the plugins folder of ImageJ. Where can you find that? So for example, here is the Fiji or ImageJ folder, Fiji app, and there's the plugins. So you will have to go and drop it here, and once you drop it there, then restart Fiji or ImageJ and you will be able to start that. So I have already put that plugin in here, and it's called iterative deconvolve 3D. Okay, so here I will put this. This is the image that you can download from our website, deconvolution image. So you can see deconvolution image TIFF, and if you see it in 3D, it has intensities like this. Okay, it's a Z stack, 630 frames, and this is the point spread function that we saw just now. So you can see that intensity increases, and there are multiple rings that you see here. So all of these diffraction patterns. Okay, so if we use these two images, we'll go here, plugins, iterative deconvolve, and the image should go here, and the point spread function should go here, normalize PSF, and leave everything else to default, and hit OK. Make sure that you are doing this process on a computer which has got at least, I would say, 32 GB of RAM, because or else the software is going to hang. This requires a lot of RAM and computation speed, and you can hear your computer's fan like running at the highest speed because it becomes very hot. Okay, so make sure that you run it on a powerful computer. Awesome. So now let's move on to the next topic, which is 3D image rendering. So this will be useful when you want to show a 3D object in space for a good publication quality image. So for example, here we got a chance to image a spheroid from Novaxians. This is a cancer cell spheroid, and you can see that it is sitting on a glass surface, and we could see actually it's sitting so nicely on the glass surface. This is actually inverted image, and we can do 3D rendering like this and put shadows and things like that. So how do we get that? So go to plugins and volume viewer. All you have to do is to start again your ImageJ, favorite software ImageJ, and open the image which is the 3D stack like this, which is here. This one has got different planes like this all the way from bottom to top. The direction doesn't matter, it can be anyone. And once you have this, then go to plugins, and there is something called volume viewer. If you click that, then it is going to open a window like this. Okay, where you can have a lot of different options. Make sure that you select volume, tricubic smooth option, and 2D MD, which is going to give you a triangle like this, and then you can click on the light. It is going to do 3D rendering, and you can adjust these parameters, the scale and the numbers and all of that. And of course, make sure that the Z aspect ratio is set to whatever number is the actual for the image. And this is again going to require a lot of RAM, and maybe if you also have a graphics card, that's even better, because I'm right now not moving it because it is going to eat up all of my memory in the computer. So Just for the sake of showing, I'm not showing it, but make sure that you do it on your computer. So using that, we can generate very nice beautiful images like this, where you can see each synaptic button here on a cell in a neuron. So whatever you want to show, it becomes very easy to visualize in 3D. Next is colocalization analysis. So for doing this, of course, make sure that your images are acquired at Nyquist sampling or whatever is necessary settings. You can find a video for how much to zoom or not, all of that details on a video on our website. Under the guides and tutorial section, there is a video there for colocalization analysis. So first watch that, acquire good quality images like as shown. Let me open that image real quick. So this is an image of endosomes of a macrophage cell line, and you can see these are labeled pretty well, and the resolution here is very high, which is the best resolution that you can achieve using that microscope. And I have put enough number of pixels so that it is being sampled on Nyquist sampling. And same way I have imaged in the other channel, which is here. You can download these two files again from the website, and once you have these two images, you can go here, analyze and colocalization, and click Coloc 2. It is going to open a window like this. You can upload these two images here. The order of it doesn't matter. What matters ultimately is whatever analysis you are doing, you do it consistently over all the images. So for example, we keep it like this. We won't use any ROI or mask right now because this image is pretty good. Had there been a lot of background, then I would maybe use a mask so that I can get rid of the background. If you want, you can email me on how to, or you can Google search on how to create a mask for the image. Okay. Then let's keep it like this. Point spread function is 2 because I have sampled it at Nyquist, and click OK. It is going to run and it is going to generate a file. You see that it is running in the background. And by the way, if you have multiple images like this to be analyzed, you can actually open multiple Fiji windows like this by double clicking on the same icon again and again, and they all can run in parallel. And here it has done the analysis. It took some time, and you can see that it is giving us some warnings because there is not a lot of pixels here, so it is saying that there are too less pixels. But overall, if you see here, it is giving me a very high colocalization value. Whichever value you want to pick up, you take and stay consistent with that. In this case, for example, we'll take this one, Pearson values below threshold, which is 0.78, which is a very high number. And you can see that when I actually merge the images. So these are the two images. I will go here, image, color, and merge channels. So for red color I will put this, and for green color I will put this. I will keep the source images, and there's the merged image. And you can see that it is nicely colocalized. Like you see the light yellow color here. Wherever you see a yellow color, that means it's colocalized. Wherever you see just a red color, it means it is not colocalized with the green. So you see there's a very strong correlation, and by looking at the image itself, you can say, oh, they are so nicely exact duplicate of each other, and that's what you see here. Now how do we prove that it is actual colocalization, not some fake number? So what do we do is we take one of the images like this, and then we will do translation. So right now, if you see, if I draw the region of interest here like this, it tells me that it is roughly how long? It's about 2.5 microns, which will be converting to I would say 15 pixels or so. So that's the largest size of the object here. So if there is any false colocalization, we'll see whether we can eliminate that. So go to image and transform and translate, and in both the axes, make it move by 15 pixels. If you preview, you will see that the image shifts 15 pixels each direction. So I will say OK, and now ideally they should not overlap. So let's see if they are going to do that. Merge channels, and again I will use the same thing, and I will say OK, and you see that now they have shifted, right? So there should be very less co-localization between the two images. Let's try that and see whether it actually is. So co-localization, colloc 2, and say OK, and same settings, everything is same, and we'll run it again. And while it is running, we can have a more zoomed in look at it. It will take some time but yeah, very soon it should show up. And while it is doing all of that analysis, let's really quick have a look here. The way to get to the translate option was go to image and translate. Okay, so we have got the answer here. Now we'll see, and now the co-localization value is close to 0 so which is perfect. So that's what we wanted, right? That earlier it was 0.78 and now it is 0. So that means whatever like result was there is actual true co-localization. So this is how you can do a co-localization analysis. And with that we come to end of module number 3, and in module number 4 we'll see how we can automate all of these steps that we have covered so far and write a code in a very organized way so that we can do the analysis by using 1 or 2 clicks. Okay.